Hello everyone. So in the last video, we have discussed about the negative sequence relay. So in this particular video, we are going to see these particular questions what is harmonic restraint relay. I have added few more questions additionally, so I'll discuss all of them. So you can just follow the lecture series. Okay. So first of all, why this harmonic restraint relay is used? So basically, this particular relay is used in transformer. Okay, harmonic restraint relay. So what happens in case of transformer? In transformer, if you switch on your transformer at no loaded condition, depending on the switching instant, you will get inrush current. Okay, so one of the videos like I have discussed, so if there can be worst case scenario and there can be some best possible ways, like best cases you can say. So if you switch on your transformer at worst case, then the induced current magnitude will be huge, and that induced current magnitude can go up to 5 to 6 times of the full load current. Okay, and sometimes although that inrush current exists for a minor durations and all, but still that current can, like, because of that high current, the overcurrent relay that we are using in transformer, that can also trip. So kind of you can say it will kind of malaporate, like, though like there is a no restriction happens because of the inrush current in transformer, but still that high magnitude current can be a trigger point for overcurrent relay. So first I will maybe briefly I'll just explain you about the induced currents and all. So as you know, the voltage is across the coil is nothing but V equal to N d phi by dt, right? Okay, if I just you can say if I just assume my the Lenz law and all, so this is how you will get a voltage magnitude. Let's say you have a transformer and it is under no load condition. Okay, and if you switch on this transformer, and then you can end up with huge no load current or huge magnetizing current, and that magnetizing current and or exciting current can be 5 to 6 times of the full load current. Okay, and this high magnitude current can be a trigger point of overcurrent relay, that also I'll discuss, but let me explain what happens. So if you see this particular equation, so if I have you can say, let's say my supply voltage VST is let's say this is my Vs of t, and my VST is nothing but a sinusoid, Vm sin omega t. Okay, so let's say I'm putting this equation into that particular Faraday law of electromagnetic induction equation. So I have n d phi by dt. I want to see the phi, how my phi will be. So if you see, you will get, if you rearrange this, you will get this. And I want to convert this dt into function of d of omega t, v of n omega sine of omega t. I have discussed this inrush current and all in one of the video. You can maybe watch that video. But again, to explain this particular relay, I should also explain these things again. Then it will be easy for you to understand. So let's say at any time t equal to t naught, you are closing this particular switch. So Vm by n omega, and at t equals to t naught, my core was like, it was fresh, there was no flux at all, so my core flux was simply zero at that t equal to t naught time. So my core flux was zero. So my closing time period, you can say omega t naught, and I want to see what will be the flux at any in general time omega t, sine of omega t, d of omega t. Okay, and at this time I have flux 0, and let's say I am having flux phi of t at any given time at t. Okay, so if you solve this particular equation, what you will get, minus Vm n omega cos omega t minus cos omega t naught is equals to phi of t, right? you will get this one. So if you see phi of t is equals to Vm n omega cos omega t naught minus cos omega t. Okay. Now, uh, see, if you switch on or this t naught time, so maybe I can use next page. So phi of t is equals to Vm by n omega cos omega t naught minus cos omega t. Let's say if I have the switching instant t naught at 0 second, then I'll be having phi t is equals to Vm n omega 1 minus cos omega t. If you draw this particular waveform, it is a kind of you can say at omega t equals to 0, this value will be 0. So it will simply start from 0. Let's say this is my phi of t, and maybe this is my omega t axis. And at omega t equals to pi by 2, it will be having this value. This is my pi by 2. This is pi, 3 pi by 2, 2 pi, let's say. So, but at uh, if you see at omega t equals to 0, here 0 value will be there. So this is my 0 value. At omega t equals pi by 2, I'll be having this much amount of value. At omega t equals to pi, I'll be having twice of this value. So it will be having here. So the waveform you will see it will be like this. Okay. So and this value is 2 by Vm by n omega. So here the value is Vm by n omega, right? Vm by n omega. So here the flux is getting doubled, and as you know, the BH curve of the transformer or any ferromagnetic material, it is not linear. So it will having the non-linear characteristics. So up to certain point it will be linear, but after that it will be non-linear. So it will be non-linear in nature. And if I draw this particular graph here, let's say I have this sort of flux. I should draw slightly more. This sort of flux waveform I have. See, B is proportional to phi and my H is proportional to current. Okay. So if you map this particular equation, so if you see like up to this point, maybe you will get the linear relationships. So here the current will also follow the same kind of structure of the or same kind of nature, you can say. So like that it will be like this, and here also my current, like till this point it will be kind of, it will follow the same nature as the flux, but here I have, but if you see from this point to this point, I have the non-linearity. So to produce this much amount of flux, I need huge current. I need huge current, and that current will be peaky, much more peaky in nature, much more peaky in nature. Okay. So like that, you will be having peaky current, and the magnitude is huge. So this current, as I mentioned, it can be 5 to 6 times the full load current. And basically, in transformer winding protections, let's say if you have a transformers, so we use to we use to protect the transformer windings and all. We basically we use overcurrent relay with the help with differential relay. So what we'll be having. Uh, let's say this is your transformer that you want to protect against any fault. Okay, so you can have a differential relay. So this is the basic structure of differential relay, and it will be having operating coil here. uh, this will be your operating coil, and since the secondary is open circuited, if this because of this huge current, this operating coil will like send a trip signal to circuit breaker, and it may trip. But practically what happens, this induced current lasts for very minute duration. Okay, and it is not even harmful. So but it can trip the you can say circuit breaker, and it can isolate this transformer, so and all. Okay, although we can use some kind of insertion resistor in transformer to limit this particular induced currents and all. But again, we can do something with the help of harmonic resistant relay. If you see the nature of this particular current, if you write the Fourier series expression for this inrush current, let's say I am considering this is my origin, let's say just a random, I'm taking the origin. So this particular origin placement and all, it doesn't affect on the harmonic analysis and all. Just instead of cosine, you may get up with sinusoidal terms. So if you write the Fourier series expression for this inrush current, you can see the nature of the this particular waveform. It is even in nature, and only you can comment on the event. So if you write the Fourier series expression, so you will get the cosine term, and also you will get the DC component, because it has the only positive quantities. So you will be having DC component and you will be having cosine components, but you cannot comment on the odd harmonics or even harmonics and all, because this particular figure does not contain the property of odd harmonic, odd half wave symmetry. Okay, so you cannot comment on that. But what has been observed, like this inrush current contains significant amount of second harmonic quantity, around 30 to 40% second harmonic quantity it can contain. Okay, whereas normal fault current, it contain very less, maybe 5 to 10% is second harmonic component of current it can contain. So we can basically utilize these two things along with the differential relay to to restrain or to restrict the operations of the relay, you can say. So let's say if you have a transformer with you and you are having differential relay or differential protections here. So let's say this is how the differential protection circuits, and you will be having some operating coils and all, and this is how, right, this is how your differential protections can operate to protect the transformers faults and all. Now what we can do, rather connecting a simple operating coils, we can design some circuitry. That circuit will basically extract the second harmonic component that are flowing in the transformer, and it will measure like what is the percentage. Is it a significant amount or it is a less amount of quantity? So if it is a significant and it lies in between 30 to 40 percentage, then my operating coil should not send any trip signal to circuit breaker. So my system, the protective system, should understand, okay, this is an inrush current, I should not send a trip signal because it is not harmful and it will go away within a moment. So I should not trip it. Whereas if there is a fault current and there is the, you can say, the second harmonic quantities lies 5 to 10 percentage, in that case my relay operating coil should send the trip signal to circuit breaker to trip the circuit. So this is how I should be able to differentiate in between fault current and inrush current. And to differentiate that particular scenario, we generally use harmonic restraint relay. The name suggests harmonic because we are taking help of harmonic to trip the circuit breaker. Restraint means, depending on the harmonic analysis, we are going to restrict the operation of the relay. So that's why we call it as a harmonic restraint relay. I hope it is clear. Still, if you have a doubt, you can ask me in the chat box. Thank you.